Yeah, this is Levik Academy. Kindly subscribe if you have not subscribed to this channel. We are discussing about group theory, and we are looking at about subgroups today. If you have not looked at the previous tutorials, kindly check them out. Remember to comment and leave any question that you may need us to tackle. Yes, we are looking at subgroup. So if we are talking about subgroups, yes, we are talking about subgroups. We say if G, we let G be a subgroup, let G be a group of a subset of G, then we say G is a subgroup, we say that H is a subgroup of G, say H is a subgroup of G if it is itself as group. So for us to, for H to qualify to become a group, this H should be itself be a group, should be a group. They should be a group. Should be a group. So that should be noted. So what are the properties of a group? That's a question that we need to ask ourselves. So that H qualifies to be a group. So equivalently, we are saying if H is a subset of G and is a subgroup of G if number one is closed and a minor operation. We are saying if there is a X and Y, which are elements of H, if you do by binary operation their product, then it will be closed. This is the property called closure property. Next, secondly, if you have a given element X in H, then its inverse should be in H. So if these two key options properties owned, then we will say that H is a subgroup of G. It's a subgroup of G. So that's basically the qualification for this. Okay, let's check about this theorem here. So let G be a group, then H is a subset of G, is a subgroup of G, to be a subgroup of G, if and only if, this is very key, if and only if, for all X, Y, for all X, Y, which are elements of H, then X inverse is in H. So that's very key to note. So our interest is just to see if you can already prove that this is true, then that gives us a direct ticket that this particular subgroup of G, subset of G is a subgroup. So to prove this, part one is that to show that H is a subgroup of G. So suppose H is a subgroup of G. That shows us that H will be, because it's a subgroup of G, and by elimination of subgroup of G, we know that number one, closure, number two, inverse should be present. So we know H is closed under the binary operation and inverse. That's a fact. So that if you have a given element of H, which is X and Y, then the inverse, which is the by inverse property, Y inverse, because Y is an element of H, it's also in H. That is by the inverse property. That will mean that again the second scenario or the condition X Y inverse will be again in H. So that is automatically noted like that. Therefore, suppose again that now the elements xy are in H and xy inverse is in H. Now what we need to show is that now this H is a subgroup, so that now our if and only if condition is totally fulfilled. So how do we show this? So we start by looking first inverse. So we let x be equivalent to equal to E, which is the identity, which is the element of H. That means if we do the first condition, and remember x now become E, so it will tell us that this is true, what we need. That's what actually we need. So for every y in H, so we are saying every y in H has its inverse, which is y inverse, by this scenario. Next condition that we need to fulfill so that this becomes an subgroup is closure. So if x and y are in H and H is in this by inverse that we have just discussed above here, we see that okay, before we proceed with this, if you have not yet subscribed, kindly subscribe. If you have not yet, click the notification bell there, kindly hit it, so that every time I post anything here or any discussion, you are the first one to get a notification. If you have a question or a comment, leave it down on the comment line, and also remember to share this with your friends. Now, because this is true from what we have discussed here is in H, then it will mean this still will hold, so that when this happens, then xy will be in H, and that means the two conditions of a subgroup have been fulfilled or satisfied, and that it will tell us that this theorem establishes that to show that H is a subgroup of H, is a subset of H is a subgroup. It is just enough to show that if there exists an element xy in H, then the y inverse, xy inverse, that's a product, is in H. The moment you show that, then automatically that particular subset qualifies to become a subgroup. So that's basically it. So for example, in this case here, if you show that, you want to show that this subset is a subgroup of this set. So if you let ungiven x, because that's what you need to show, be m1 over n1, and you let ungiven y be equal to m2 over n2, okay, all these to be in the subset. This should be the one with the basis under multiplication without 0, so that we expect us to have the what we need. So what you need to show here, so that this qualifies to be a subgroup of this, is to show x y inverse. So what is y inverse? It will mean that our y inverse is basically n 2 over, because this is the inverse of this. Yeah, remember in this case, neither of n1, n2, okay, is 0. They are non-zero. Even m1 and m2 are non-zero. They are non-zero. So if you do this, which is x, because this is what we need to do by what we have discussed here. This is our m over n1, n2 over m2. So you can see this is giving us m1 n2 over m2 n1, which is actually in group in the subset. So by this, because this is giving us this, so by that fact it means that this particular subgroup, subset, is actually a subgroup of this set. So if you have any question on either of these, kindly leave a comment. I will be able to check on it and guide you on how we can play with these tricks. So until next time, we can say thank you for your time.